All right, let's talk about your flight instruments. This will be very important to discuss for your check ride. First, the pitot system. What instruments operate from the pitot system? All right, so what we're talking about here, it's your altimeter, your VSI or your vertical speed indicator, and your ASI or your airspeed indicator. So what do we have here? We have three instruments on the pitot system: altimeter, VSI or vertical speed indicator, and airspeed indicator or ASI. All three instruments receive static air pressure for operation, with only the ASI receiving both pitot and static pressure. So only your airspeed indicator is both pitot and static. All right, how does your altimeter work? So your altimeter is a sensitive altimeter, which means it's an aneroid barometer that measures the absolute pressure of the ambient air and displays it in terms of feet or meters above a selected pressure level. The sensitive element is a sensitive altimeter, which is a stack of evacuated corrugated bronze aneroid capsules. The air pressure acting on these aneroids tries to compress them against their natural springiness, which tries to expand them. The result is that their thickness changes as the air pressure changes. Stacking several aneroids increases the dimension change as the pressure varies over the usable range of the instrument. What type of errors is your altimeter subject to? What could cause your altimeter to display erroneously? One would be a mechanical error. So differences between ambient temperature and or pressure can cause an erroneous indication on the altimeter. Inherent errors, so non-standard temperature and pressure, like warmer than standard air. The air is less dense and the pressure levels are farther apart. So let's talk about this. Let's break this down. Warmer, colder, and extreme. We're looking at 1, 2, 3, 4, 5 inherent errors. Warmer than standard air, colder than standard air, extreme cold altimeter errors, high pressure to low pressure, and low pressure to high pressure. So let's break this down. We have 1, 2, 3, 4, 5 inherent errors with your altimeter. And the warmer than standard air, the air is less dense and pressure levels are farther apart. The pressure level for a given altitude is higher than it would be in air at standard temperature, and the aircraft is higher than it would be if the air were cooler. True altitude is higher than indicated altitude whenever the temperature is warmer than ISA, or International Standard Atmosphere. Now, colder than standard air. So in this case, the air is denser and the pressure levels are closer together. The pressure level for a given altitude is lower than it would be in air at standard temperature, and the aircraft is lower than it would be if the air were warmer. True altitude is lower than indicated altitude whenever the temperature is colder than ISA. All right, extreme cold altimeter errors. A correctly calibrated pressure altimeter indicates true altitude above mean sea level. When operating within ISA, International Standard Atmosphere parameters of pressure and temperature. When operating in extreme cold temperatures, so we're talking about 10 degrees Celsius to negative 50 degrees Celsius, pilots may wish to compensate for the reduction in terrain clearance by adding a cold temperature correction. High pressure to low pressure. If an aircraft is flown from an area of high pressure to an area of lower pressure without adjusting the altimeter, the true altitude of the aircraft will be lower than indicated altitude. High to low or hot to cold, look out below. Lower pressure to higher pressure. If an aircraft is flown from an area of low pressure to an area of higher pressure without adjusting the altimeter, the true altitude of the aircraft will be higher than indicated altitude. Again, high to low, look out below. or hot to cold? Look out below. All right, for IFR flight, what is the maximum allowable error for an altimeter? And this would be good to put in your pre-flight, not your pre-flight, just your taxi check before you depart. If the altimeter is off field elevation by more than 75 feet, with the correct pressure set in the Colesman window, it is considered to be unreliable. So 75 feet, that's a pretty good margin of error, which of course gives, pressures might be changing kind of quickly. So it's likely that you will find yourself often like 25 feet off or something. All right, so 75 feet is the maximum allowable for your altimeter. Define and state how to determine the following altitudes. All right, so let's ask this. What kind of altitudes are there? There are 5 types. What are the 5 types of altitude we talk about in aviation? This goes back to your PPL training. Indicated altitude, true altitude, absolute altitude, pressure altitude, and density altitude. Let me say this again. These are the 5 types of altitude. Indicated, true, absolute, pressure, and density. Now, your indicated altitude is the altitude read directly from the altimeter without being corrected after it is set to the current altimeter setting in the Colesman window. All right. So once you've set your altimeter to the 30.3000, if that's what it happens to be, instead of 2992, your indicated altitude, that's what we're talking about. Your true altitude is the vertical distance of the aircraft above sea level. So your altitude MSL. Airport terrain and obstacle elevations on aeronautical charts are all true altitudes. Absolute altitude. That is the vertical distance above the terrain, or basically AGL, above ground level. Your absolute altitude is AGL. An altimeter set to the proper pressure reading indicates 0 feet at touchdown. It is referred to as QFE. All right, pressure altitude. Indicated altitude with altimeter set to 2992 inches of mercury. That's what your pressure altitude is. When you set 2992 inches of mercury in the Colesman window, what you read is your pressure altitude. Pressure altitude is used to compute density altitude, true airspeed, and other performance data. Now your density altitude. That's your pressure altitude corrected for variations from standard temperature. All right, this becomes especially important, of course, in warm months when the heat can really seriously negatively affect the performance of your airplane. Does adjusting the altimeter's Colesman window have any effect on the altitude that is displayed to an ATC controller? So when NorCal Approach or wherever you're at says Stockton altimeter 2999 inches of mercury, 2999. Okay. And I set that. Do they see that I have set that? No. The encoding altimeter measures the pressure reference to 2992 inches of pressure altitude and delivers this data to the transponder. When you, the pilot, adjust the barometric scale to the local altimeter setting, the data sent to the transponder is not affected. This is to ensure that all Mode C aircraft are transmitting altitude data referenced to a common pressure level. ATC equipment adjusts the displayed altitudes to compensate for local pressure differences, allowing display of targets at correct altitudes. Now, this might be something to be worth kind of touring an ATC facility to see this, but your altitude may be showing something different than what you tell them. If you're flying at 3,000, but it looks like you're at 3,001, they may ask you what your altitude is, and they may give you a reminder of what the correct altimeter, pressure setting should be in that case. All right, how does the airspeed indicator operate? How does your ASI operate? The airspeed indicator measures the difference between ram pressure from the pitot head, right from the pitot tube, and the atmospheric pressure from the static source. So what are we talking about here? So in your pitot-static system, that's the only instrument of the 3 pitot-static instruments that uses both ram air and static pressure. What are the limitations the airspeed indicator is subject to? It must have proper flow of air in the pitot-static system. If there's anything affecting static air or something, it's going to affect your reading. Also, if there's any blockages in either your pitot tube or your static port, you will have problems. What are the errors that the airspeed indicator is subject to? Position error is one, caused by the static port sensing erroneous static pressure. The slipstream flow causes disturbances at the static port, preventing actual atmospheric pressure measurement. It varies with airspeed, altitude, configuration, and maybe plus or minus value. All right, that's your position error for the position of the actual static port. Density error. Changes in altitude and temperature are not compensated for by the instrument. Compressibility error, caused by the packing of air into the pitot tube at high airspeeds, resulting in higher than normal indications. It usually occurs above 180 knots indicated airspeed. That's your compressibility error. All right, what are the different types of aircraft speeds? Indicated airspeed would be one, IAS. IAS is shown on the dial of the instrument, uncorrected for instrument or system errors. That's your indicated airspeed. Your calibrated airspeed, or CAS, is the speed at which the aircraft is moving through the air, which is found by correcting the IAS, or indicated airspeed, for instrument and position errors. Your POH, or AFM, does have a chart or graph to correct indicated airspeed for these errors and provide the correct calibrated airspeed for the various flap and landing gear configurations. Your equivalent airspeed, or EAS, the EAS is the CAS, or calibrated airspeed, corrected for compression of the air inside the pitot tube. EAS, or equivalent airspeed, is the same as calibrated airspeed in standard atmosphere at sea level. As the airspeed and pressure altitude increase, the CAS becomes higher than it should be, and a correction for compression must be subtracted from the calibrated airspeed. All right, finally, true airspeed, TAS. TAS is CAS corrected for non-standard pressure and temperature. Let me say that again. True airspeed is calibrated airspeed corrected for non-standard pressure and temperature. True airspeed and calibrated airspeed are the same in standard atmosphere at sea level, but under non-standard conditions, true airspeed is found by applying a correction for pressure, altitude, and temperature to the calibrated airspeed. So what do we have here? Let's summarize. There are 4 types of airspeed: indicated airspeed, calibrated airspeed, equivalent airspeed, and true airspeed. Let's talk about airspeed indications. What airspeeds are indicated by the various color codes found on the dial of an airspeed indicator. Right, the white arc. Think if you can remember this. What does the white arc represent on your airspeed indicator? The length of that white arc is your flap operating range. The lower limit of that white arc is what? First of all, it's VSO. If we're thinking in V speeds, it's VSO. The lower limit of the white arc is VSO. And that's the stall speed or minimum steady flight speed in landing configuration. So gear and flaps down. Think of it as a countdown to zero, VSO, or VS0, VSO. All right. And then so from that, what is VS1? Where could we find VS1 and what is VS1? VS1 is the stall speed or minimum steady flight speed obtained in a specified or clean configuration. That's going to be the lower limit of your green arc. What is the green arc? The green arc is the normal operating range. Okay. Upper limit of the white arc. Back to that white arc. Remember, the white arc is the flap operating range. Your maximum speed with the flaps extended, or VFE. FE for flaps extended. That's the upper limit of the white arc. Maximum speed with the flaps extended. What's the upper limit of the green arc? The upper limit of the green arc. The upper limit is VNO, or the maximum structural cruising speed. Do not exceed this speed unless you are in smooth air. So don't go into the yellow unless you're in smooth air. Now, something to think about. That green arc doesn't have a V speed attached to or anything like that. Just the same with the white arc. Excuse me. Normal operating range. When you think about operating ranges, there's not a V speed there. So the NO, don't be confused and think NO is normal operating, except for the fact that it's like the maximum of the normal operating range. So the upper limit of the green arc is VNO, maximum structural cruising speed. We talked about that yellow arc. What is that? That's simply your caution range. You can fly within this range, but only in smooth air. And even then, only with caution. All right, red line, VNE. I know we remember this, but if not, you could figure out what NE means. Never exceed speed. VNE, that's the red line. Do not exceed this speed. Operating above this speed is prohibited. It may result in damage or structural failure. Sounds terrifying. Okay, how does the vertical speed indicator work, or your VSI? Now, this is also part of the Pitot static system, but it doesn't use ram pressure. This is only going to use your static pressure. The VSI is a rate of pressure change instrument that gives an indication of any deviation from a constant pressure level. Inside the VSA instrument case, there's an aneroid, okay? Both the inside of the aneroid and the inside of the instrument case are vented to the static system. The case is vented through a calibrated orifice that causes the pressure inside the case to change more slowly than the pressure inside the aneroid. So it's a calibrated leak. Changing pressures inside the case and the aneroid compress and expand the aneroid, moving the pointer upward and downward, indicating a climb, a descent, or level flight. Okay, let's summarize the Pitot static system. We have three instruments: the airspeed indicator, the vertical speed indicator, and your altimeter. One of these uses both the ram air and the static air. And that is your airspeed indicator. Your altimeter and your VSI only use the static pressure. What are the limitations of the vertical speed indicator? It's not accurate unless you're stabilized. Sudden or abrupt changes in the aircraft attitude will cause erroneous instrument readings as airflow fluctuations over the static port. These changes are not reflected immediately by the VSI due to the calibrated leak. So you just got to wait for the air to actually leak before you can get a correct reading. While en route in IMC, ATC clears you to climb to a new altitude. After establishing the appropriate pitch attitude and power setting, your altimeter and VSI correctly indicate a climb but your airspeed indicator indicates that your airspeed is increasing. What might be the problem? All right, so let's say this again. You are, ATC clears you to climb to a new altitude. You are establishing the climb, the appropriate pitch, attitude, and power setting. Your altimeter and VSI are showing as they should. You are climbing. But your ASI, your airspeed during the climb, indicates that your airspeed is increasing. This shouldn't be happening. We know that when you climb, unless you've added a significant amount of power and a lower nose attitude, there's no reason why you should be increasing airspeed. So what's the problem? Moisture, insects, other foreign matter, something has caused a pitot tube blockage. The pitot tube itself is blocked. If the pitot tube ram pressure hole and drain hole, because there's two holes in the pitot tube, if they have both become obstructed, the airspeed indicator operates like an altimeter as the aircraft climbs and descends. During a climb, the airspeed increases. During a descent, the airspeed decreases. The danger is that a pilot will not recognize the problem, and during a climb will attempt to reduce airspeed by increasing your pitch attitude or reducing power, and it could result in a stall. All right, on takeoff, as you climb away from the runway into IMC, you notice that your vertical speed indicator is indicating 0. You're climbing, but your VSI shows that you are level. Your airspeed indicator is still alive, but doesn't seem accurate, and the altimeter is completely frozen. So again, you're climbing, and you're going into IMC, but you should know, if you have visual reference, you know you're climbing, but your altimeter is showing that you are not. It's just stuck. What's the problem? All right, so here the static system is blocked, and you would observe the following. Your airspeed indicator is accurate at the altitude where it became frozen. So if it got blocked, if the static port was blocked at, say, 1,000 feet, that's where it's stuck. So as long as you're at 1,000 feet, it will be accurate. Otherwise, it's just stuck at 1,000. If you descend, the airspeed indicator would read high. Outside static pressure would be greater than that trapped. If the aircraft climbs, the airspeed indicator would read low. Your altimeter indicates the altitude at which the system was blocked. It's stuck there. Vertical speed will indicate level flight. If the air temperature is plus 6 degrees Celsius at an airport elevation of 1,200 feet, and a standard or average temperature lapse rate exists, what will be the approximate freezing level? So you really kind of want to do some basic math on this one. All right, 6 degrees Celsius. You're at 1,200 feet on the ground, and it's plus 6 degrees Celsius. And you have a normal temperature lapse rate. Where does freezing level begin? It's going to begin. Well, let's do this. 6 degrees at the surface divided by the average temperature lapse rate of 2 degrees Celsius results in a 3,000 foot freezing level. And convert it to sea level by adding the 1,200 foot airport elevation, we get 4,200 feet mean MSL, mean sea level. All right, what corrective action is needed if the pitot tube freezes or if the static port freezes? So for the pitot tube, just turn the pitot heat on. We're talking about a freeze here, not like a bug that flew into it. For your static system, use alternate air if available. If that's not working, you can always break the glass on the VSI. The VSI is not required for instrument flight, and breaking the glass provides the altimeter and the ASI a source of static pressure. What instrument indications should you expect to observe should it become necessary to use an alternate source of static pressure? All right, in many unpressurized aircraft equipped with a pitot tube, an alternate source of static pressure is provided for emergency use. If the alternate source is vented inside the airplane, where static pressure is usually lower than outside, so cabin air is usually lower pressure than outside, selection of the alternate static source may result in, start with the altimeter. Altimeter will indicate higher than the actual altitude. Airspeed will indicate greater than the actual airspeed. Vertical airspeed will show a momentary climb and then stabilize if in level flight. Kind of probably a way to remember this is the pressure's lower, but everything increases. Altimeter increase, airspeed increase, VSI increase. Everything is an increase when you use the alternate static pressure.